Hello and welcome to our final Fed presentation. Our group, we're hog savers. We did the river project for Fed, and this is our presentation.
Yeah, for our ideation, so we had a few challenges. The aim for the project, create something not necessarily ordinary, but that would still be effective if it was used in the environment. We wanted to incorporate the runs in the pools that you would see like in the rivers where the fish that we were trying to simulate like their environment live. And we wanted to use materials that would be like natural, like in a river and that type of habitat. A few other things, we wanted to be able to create areas for the water to stall so that it would make it easier for the fish to like swim up. We also wanted the run-like areas for fish to move through the structure quickly and efficiently, obviously because we want our design to be as efficient as possible for the fish. We also wanted to have a downhill slope to the top face. And we wanted to go for a design that could seamlessly integrate into the environment. So if we were to use it, it wouldn't be awkward or look out of the ordinary.
Yeah, so for our first iteration, had a lot of problems. Wasn't super ideal, obviously, because we didn't really have any 1.3 centimeter holes through it. We tried to go with the like the kind of stilt on the bottom to try and break up the water as much as possible, stop it from accelerating so much, and also allow for fish to kind of be able to flow over the top, but then slow the water to the bottom so that they can just kind of weave their way through there. And then also we just had this like curved face on the back of the structure to try and pool water even more so that, when fish came out of the bottom here, or when fish were getting ready to go over the top here, they kind of had somewhere where they could just like stall and not really be like swept over the top or pulled under the bottom. But there were really big issues with that one, mainly that these square pillars caused really turbulent water when we fluid tested it in SolidWorks. And so we changed our design in the second iteration to have like circular pillar stilts on the bottom. Obviously, we're still lacking the big hole component. We were just trying to take it step by step and just try and figure out ways that we could slow the water down through the bottom first, and then we were going to come back and figure out the whole section of the problem. We didn't change much about this, like the cavity feature at all, really. But when we were doing flow testing, these pillars didn't really seem like they were like being super effective on the bottom. It honestly seemed like it was just a little bit too much. So we thought about, because they're not even staggered or anything, it's just like basically just creating a straight that would accelerate the water instead of break it up like we'd hoped. So we instead decided to just kind of scrap everything. And I think Tom ended up coming up with this fusion model when we were having a little ideation session one time. And Matt drew this graphic to kind of bounce off what Tom had. But Tom's idea here was to integrate weirs on the top of our structure so that we kind of could hold the water, pool it, and then send it over like the, very slanted, like nice face to kind of create an area for fish to rest as they're going up or down the structure. And then more offset pillars on the top to actually break up the water flow instead of creating a straight where it just accelerates the water even faster. And then Matt kind of bounced off that and was like, oh, well, we could like, make the slant even less so the water accelerates even less as it comes down the structure, and add these holes through it, to simulate the runs in a river. And so then our iteration 3 was born from those ideas. So we took the pillar idea and kind of apply it to the top. These weren't really these weren't well spaced at all, which is another problem that we'll address later. But we did integrate a nonlinear weir on the front of our structure, because nonlinear weirs are more effective at holding more water back because they have more like surface area for the water to like push up against. Weirs have a lot to do with geometry, but this one's just really effective at creating a nice pooling area for the fish to kind of chill out in before they either go over or continue back upstream. So we flow tested these iterations pretty heavily and found out that our holes, while they were 1.3 centimeters at our inlet volume flow of 16 or 1.6 liters per second, which is this is just a metric equivalent. It was really fast through here, almost too fast. Like I think it was 3 meters per second the water was coming through here, so we really needed something to, because this bottom hole, the idea for this bottom hole was that fish would be able to get back upstream through this hole. So obviously, I don't know what kind of fish is going to be able to swim faster than 3 meters per second in the opposite direction, still go forward. So, oh, and then this is just more statistics from our flow testing where we, more statistics from our flow testing where we just kind of wanted to look and see, like, from the time the flow initially started to the time it was fully developed, how the velocity would kind of how the velocity would adjust. So then from all that testing, iteration 4 was born, and as you can see, we made the pillars a lot more evenly spaced. We made them spaced 1.3 centimeters apart on all sides, so fish could swim in between them freely. And we also drafted the hole on the bottom by 2 degrees outward in order to really slow down the water. And you'll see how that comes into play here in a minute. But another big feature that we changed was we used a spline or spline to kind of create this back curved surface, and we just moved our focal point of that curve down because it created a more effective pooling region. It created a more effective pooling region back here at the top, which is kind of what we were going for. And then, so for the flow testing of our final iteration that we did, this is what the flow looked like over the top of the structure. And so this is the trajectories placed over a cut plot of the velocities. And as you can see, as the water hits the barriers and comes down right in front of the weir, it really gets slowed down right here. It's super effective at doing that. And then it also slows it down right after for the fish, to kind of like pour off into here to continue on downstream. And then, so for the 4th iteration, also here, this is where we did the flow testing of our tubes, and you can see trajectories and cut plots on the 2 different pictures here. And so we split the reason why you see 0.004 here instead of 0.16 is because we split the 0.16 between 4 different holes. So in all, we're still getting 1.6 liters per second through our structure. And so as you can see, the velocities are a lot less here. We got them well under a meter per second by drafting this hole outward, which was really, we like that a lot because obviously fish are going to be able to get back through here more efficiently and with less effort. But also coming through the top, they're not going to be thrown out so fast right into the pooling area. It's going to kind of be like a more gradual entrance to the pooling area if they decide to swim through the structure. And then also it kind of keeps the water in the pooling area calmer for when the fish come out. And then this is just more plots where we also tested for iteration 4, we tested what the turbulence looked like through the holes. And as you can see, it was high while the flow was developing, but once the flow was fully developed, as it would be in a river, the turbulence kind of leveled off to pretty much, normal, like maintainable levels that like wouldn't really mess with a fish, who's obviously like an adept swimmer because it's a fish. And these plots are just of our average velocities and fluid densities. And this is the final render of our design. For the material, we decided to go with a white concrete because it's like a rock hard, not white, but like a gray whitish, because it's a rocky material that they're already used to seeing in there because of the weir. So it kind of already is like situated within their environment, and it'll be somewhat more natural when they come across it through the stream. They're like, okay, we've kind of seen stuff like this before, and they won't be like afraid of it, swim away from it. And then obviously, as they see that this is something that they can an obstacle they can move around, they become more conditioned to it. And also we also chose concrete because it's a very like used and like well tested and well known environmental material. So we figured that would be the safest bet to ensure that we don't cause any huge environmental damage to wherever we would be implementing this structure, because we obviously wouldn't want to remove a weir to the environment and put something else there that's like a toxic material for the environment, that actually kill the fish instead of just obstructing the habitat.
So how did we meet the requirements and objectives of our design? We wanted to do our best to replicate the wolfpack fish's habitat, and we did a lot of research involving pools, runs, ripples, and the overall texture that they face. So we did our best for each structure on our final design. We wanted to replicate one of those in some way. We have the pools, the runs, and at the top, a little bit more turbulent flow created kind of a ripple effect that would be more natural for the fish, as well as slow down the water and allow for passage both ways.
So we have some challenges that we faced in this design. First, we had read through the project description a few times, and since it was a new project, we had to schedule times to meet up with the guru for more information, but we still had a hard time wrapping our heads around what exactly we needed to design. It took a lot of everyone discussing their own ideas of what we need to do before we started researching and designing. Also, it was difficult and tedious to work with the size constraints of the project and the CAD software. For example, the nonlinear weir on the top of the structure, you wanted to have full equilateral triangles, and it took time and some calculations to get everything the perfect length. We also had kind of a roadblock when it came to testing our design. It took a lot of time and research on the CAD software so we could figure out how to test the fluid flow of our structure. But we persevered and were able to make the adjustments to our design after we figured it out. We had no control over COVID being a thing, but it also has challenges like not having a real physical design to test. We had to hold online meetings because everyone could not meet in person, and everyone had conflicting schedule times, but we communicated with each other in order to make time to work on the project together. Also, we had no control over FEDD Day being online, but there were many technical issues not foreseen that had to be handled and dealt with on the fly.
Okay, and as far as how we did it, FEDD, it was a little lackluster in the fact that it was online. We didn't really have that many peers come through and visit. We had a couple, but overall it was kind of insignificant. But with the interaction with the judge, we could determine that we did a good job meeting the project requirements. We felt that the design cycle was intriguing to the judge and reflected the importance of iterative design. And lastly, the questions imposed by the judge implied progress for our own edification of the design process and the challenges for the river project in specific. And for next year students, I hope it'll be in person for you guys. I feel like as far as peers visiting the booth, it's kind of a lot easier if you walk by and you see something interesting and go up to it. But for next year, definitely research the project beforehand, before you pick one. Ask a lot of questions about the project's criteria and setup. have everyone come up with a few designs separately so you can kind of incorporate the best ones of each. Communicate clearly with your team. Make sure you really understand the projects that you're tackling and the goals of the project that you need to address. And then, of course, schedule times that work best for your group.
So thank you for watching our final presentation, and have a good one.